Welcome back, everyone, from the coffee break. I think that's what it was on the schedule. So our first talk after the break is by Elena Bogliolo of the University of Pisa, who will be telling us about stable commuter length. So take it away.
Thank you. Thank you for the introduction, and thank you for inviting me. So the goal of the next about 25 minutes will be talking about stable commutator length. And I'm sorry, there's things appearing. Okay, sorry. We'll be talking about stable commutator length, and in particular, we will try to give a sketch of the proof of a vanishing result for the stable commutator length of verbal wreath products. Okay, so stable commutator length is an invariant that you probably have already heard of. It is a real valued invariant for groups, and it allows for three definitions that come from these three different areas of mathematics, which are more algebraic, a more topological, and a more analytic definition. And this triple nature of the stable commutator length is one of the reasons why it appears so often, in particular in geometric group theory. The idea of stable commutator length is to measure how far a group is from being abelian. So in order to define stable commutator length, we start by defining commutator length. Given a group G and an element in the commutator subgroup, we define the commutator length that is denoted with CL of the group G as the least number of commutators whose product is G. Now, the stable commutator length of G in the commutator subgroup is the limit. Stable commutator length of G is equal to the limit for n that goes to infinity of the commutator length of the n power of G divided by n. Okay, now we say that a group has vanishing, G has vanishing stable commutator length, and we can also denote it with stable commutator length of G is equal to 0 when the stable commutator length of each element in the commutator is equal to 0. Okay, so just to see an example of the fact the stable commutator length is an invariant that is hard to compute, I wrote down this example by color that showed that the stable commutator length of the commutator of A and B in the free group in two generators is equal to 1/2. And the way to show it is by saying that the commutator length of the nth power is equal to the lower integer part of n divided by 2 plus 1. And an actual example is the fact that the third power of the commutator of A and B can actually be written as the product of two commutators. And I think this is not that easy to see at first. Okay, so as I was saying, in general, stable commutator length is an invariant that is very hard to compute. So one way to compute it is by relating it to other mathematical objects. In particular, we want to relate it to quasimorphisms, which are objects that appear also in geometric group theory. And through quasimorphisms, we relate stable commutator length to another group invariant that is bounded cohomology. So first of all, let's recall the definition of quasimorphism. So for a group G, a quasimorphism of G is a map from G to the real line, for which there exists a finite constant D, such that the difference between the sum of the image of G1 and the image of G2 and the image of the product of G1 and G2 is lower or equal than D for every two elements in G. So a quasimorphism, as the name suggests, is a group map that behaves almost as a group homomorphism, and it is a group homomorphism when D can be chosen to be equal to 0. We say that a quasimorphism is homogeneous when it behaves as an homomorphism on cyclic subgroups of the group G. Now, the relation between quasimorphisms and stable commutator length is given by this theorem by Bavard, namely Bavard duality theorem, that states that for an element G in the commutator subgroup, the stable commutator length of G is equal to 1/2 the supremum of this quotient, where the supremum is taken over the F homogeneous quasimorphism and we also ask that is not an homomorphism. And with df, we define the lowest d for which the inequality in the definition, so this one, the inequality holds. Okay. And when we take the supremum over the empty set, we say that the supremum is 0. This is just, yes. Okay, now the relation between stable commutator length and quasimorphism allows us to find a relation between stable commutator length and bounded cohomology. And this is important in our case because we use known result in bounded cohomology in order to find vanishing result for the stable commutator length for some groups. So the relation between bounded cohomology and stable commutator length is the following. We have that whenever a group G has a trivial second bounded cohomology with real coefficients, then it also has a trivial stable commutator length. For those who are not familiar with the definition of bounded cohomology is an analytic invariant that is similar to group cohomology, but instead of taking all the G invariant functions, we only take the bounded ones with respect to the supremum norm. So we consider these L infinity spaces, and the action is the same as usual. So if G is in G and F is in L infinity, the action is going to be this one. So GF, G to the minus 1, G0, G to the minus 1, Gn. And the boundary operator is also the same one. So G0, Gn plus 1 is going to be sent in the alternating sum of F computed in G0, Gi at Gn plus 1. And as always, we consider the homology of this cochain complex, which is the quotient of the kernel of the boundary operator with the image. Okay, so the idea is that through bounded cohomology, we find examples of groups for which stable commutator length vanishes. So some known examples are, for instance, amenable groups. This is a result by Johnson that states that amenable groups have vanishing bounded cohomology in every degree and with a very large class of coefficients. Another result that one might be interested in is the vanishing of stable commutator length for groups with commuting conjugates. This is a result by Fournier, Fazio, and Loda. And for instance, an example of a group with commuting conjugates are boundedly supported homomorphisms of R with no global fixed points. And finally, the example we're most interested in are restricted wreath products. So what are restricted wreath products? For a group G and a group A, we denote with G this little S A, the semi-direct product of A copies of G with A. And in this case, the requirements are that A must be amenable and countable. And we want the action of A on the direct sum to be by shifting of the coordinates. Okay, so the goal of this talk is to extend this result by Monod in two different directions. So we want to find, we want to have still the vanishing of stable commutator length, but we want to have it for wreath products for a larger class of wreath products. So we want to extend this result both on the right by having less constraints on the group A. So we want to allow also non-amenable groups. And we want to have to allow for other group operations on the right. So on the left, for other group operations. Okay, so which are these group operations that we want to include in this result? These are verbal products. Okay, so let's see what verbal products are. The idea behind verbal products is to define group operations that behave similarly to direct sums and free products. So we want these operations to be commutative, we want them to be associative, and we also want the resulting group to contain copies of the factors as subgroups. So this is the idea of why they were defined. In order to define verbal products, we need to define verbal subgroups. So we denote with F infinity the free group in countable generators, and consider any subset of F infinity. Then for a group G, the verbal subgroup that we denote with WG is the subgroup generated by the evaluation of the words in W with elements of G. Okay, so what does it mean? It means that if we have a word in W, this will be a word in, let's say, 10 letters. Then we take 10 elements of G and we substitute the 10 elements of G in the 10 letters that we had in the word in W. Okay, now the verbal product of two groups G and G prime with respect to a subset of F infinity is defined, we denoted with asterisk and W on the top, and is defined as the quotient between the free group, the free product of G and G prime divided by the intersection of the commutator subgroup of G and G prime and the verbal subgroup of the free product. We give the analog definition also for countable factors. So if we consider countable groups GI, then we define the verbal product of these GIs as the quotient of the free product of the GIs divided by the intersection of the commutator subgroup with the verbal subgroup. In this case, the commutator subgroup among these countable groups is defined as the normal subgroup generated by the commutators GI, GY, where GI is in GI, GY is in GY, and I is different from Y. Okay, so to have some intuition on what verbal products here are, let's see some examples. First of all, I want to show that verbal products do indeed include free products and direct sums. So let's see, for instance, that if I consider as W the empty set, then the verbal subgroup associated to the free product is going to contain only the trivial element. And so from the definition, we get that the verbal product of G and G prime is going to be just the free product of G and G prime. And on the opposite end, if we consider as W the subset containing only the word in one letter, then the verbal subgroup associated to the free product is going to be the free product itself. Then we have to consider the intersection with the commutator subgroup from the definition. And so what we obtain is that the verbal subgroup associated to this W is just going to be the direct sum. of G and G prime. Okay, so some less trivial examples. If we consider as W the subset containing just the word NK, where NK is defined inductively, then the resulting group is going to be called K-nilpotent. Okay, it's called K-nilpotent product. And the verbal subgroup associated to this W is going to be the, well, you can tell that it's going to be the lower central series. And I want to point out that in this case, the product that we obtain is not in general nilpotent, but it has a permanence property. So this product has a permanent property, which means that if we take nilpotent groups, then the nilpotent product is going to be nilpotent. And similarly for the Burnside case. So in this case, if we consider the subgroup, the subset W that contains only the word x to the power of k, then the verbal product is going to be called K Burnside product. And the verbal subgroup associated to W is the K Burnside subgroup, is the Burnside subgroup of the free product. Okay, so now you can probably guess what the definition of verbal wreath product will be. So, so we have that the verbal wreath product of G and H is just going to be defined as the verbal product with respect to W of H copies of G, semi-direct with H, and we denoted with the same symbol, but with the W on top. Also, in this case, the action of H on the copies of G is by shifting the coordinates, and this is allowed because the denominator is invariant with respect to the action by shifting the coordinates. Okay, so we now have all the elements to be able to state the result that we want to prove. So the result is the following: whenever we have a group G and a group H, we require both groups to be countable and discrete. If we have a subset of W, a subset W of F infinity that is non-empty, and if H has vanishing second bounded cohomology for a large family of dual Banach coefficients, then what we have is that the verbal wreath product of G by H with respect to this non-empty W has vanishing stable commutator length. Okay, so with this result, we can find new examples of groups that have a vanishing stable commutator length. So for example, this allows, as an example, every group of this form, G verbal wreath product with Z. This has a stable commutator length equal to 0. This is because Z is amenable because it's abelian, and so in particular it has vanishing second bounded cohomology, so it satisfies the hypothesis SU. But also, I was saying that I wanted to extend the result both on the left, so with allowing for other products, and also on the right. So in order to allow it on the right, we can see that with this result, we have also the vanishing of the stable commutator length for groups of this type. So we consider the verbal wreath product between the group G and the wreath product between G and Z. We can also have another group, G prime. This doesn't change the result. This is allowed because this group has property 2, but this extend the result by Monod because this group is not, but is not amenable when G prime is not amenable. Okay. Finally, in the last 5 minutes, let's try to have an idea of how this result is proven. So here I recall the conditions that we have. Here, once again, the hypothesis of V is very vague just because it's very technical. So in order to prove the theorem, we need 2 results, one of which is by Caligari and states that if a group G satisfies a law, then the second bounded cohomology of G with real coefficients is equal to 0. For a group to satisfy a law means that there exists a word W that is different from the trivial element in a free group F, such that for every homomorphism F from F to G, the image of W is equal to the trivial element. And this theorem is the reason why we require the subset W of F infinity to be different from the empty set. And the second result that we need is the fact that whenever we have a wreath product between a group G and a group H with the hypothesis of our theorem, then the second bounded cohomology of this wreath product with real coefficients is also equal to 0. Okay, now let's combine theorem 1 and theorem 2 to obtain the main result that we want to show. So the idea is this. Consider the projection from the verbal wreath product to the non-verbal wreath product of G by H. Then one can show that the kernel of the projection has a law. And so, by theorem 1, we have that the second bounded cohomology of the kernel of P with real coefficients is equal to 0. Now, this allows us to apply a theorem that by Moraschini and Raptis that states that whenever we have a group projection with a kernel with vanishing second bounded cohomology, then we have the following isomorphism. The second bounded cohomology of the domain is isomorphic to the second bounded cohomology of the codomain with real coefficients. But the second bounded cohomology of the codomain is equal to 0 because of theorem 2. And by Bavard duality, we obtain that the stable commutator length of the verbal wreath product of G by H is equal to 0. And this concludes the proof. I also want to point out that theorem 2 is the reason why we need a requirement on the vanishing of the second bounded cohomology for H, also for other coefficients, which are different from R, so for a larger class of coefficients. And theorem 2 is basically the proof of theorem 2 is very similar to the proof of Monod's result, But in order to allow for, so the difference between theorem 2 and theorem by Monod is the fact that we allow H to be non-amenable. And so in the proof copies, let's say, the theorem, the proof of Monod, but in order to allow for non-amenable groups, we need to use some results that come from the theory of spectral sequences. And this is everything that I wanted to say.
Okay, thank you for your talk. Let's thank Elena for her talk. Are there any questions for the speaker?
Yeah, could you tell more about the law for the kernel? Is it like something that comes from the actual words you pick for your verbal root products, like or something like that?
Yes.
Or how
Yes,
does it work?
so in fact, you can tell that the definition of having a law is very similar to the definition of the verbal subgroup, and it does come from that. I don't exactly know how to show it in an eloquent way, but yes, in fact, also as I was saying, the fact that we require the set W to be non-empty, it's basically is the same thing as asking for the law to be different from the trivial word. So yes, it comes from there.
I see. Thank you. And okay, so it does not work when you have just like the free product and then you take the semi-direct.
Exactly. No, it doesn't work
Okay.
with the free product.
Okay. But you have is there a counterexample for this or?
Let me think. I think yes. I'm not totally sure with the vanishing of stable commutator length. But I'm sure that the proof does not work at least this proof does definitely not work in the case of a free product. I don't know if I can come up with an example for the vanishing of stable commutator length. But I can think about it, and in case maybe I can send you a message or an email.
Oh yeah, I think no, I mean it's just pure curiosity. So like don't take it as as something you have to do. It's like
No, it's interesting.
Thank you.
Are there any more quick questions for the speaker? Okay, if there are no more questions, let's thank Elena one more time.